Good day, students. Welcome to mathgoodserve.com. In this clip, we're going to be going over problem 1 of the 2007 free response questions for the AP Calculus exam. And this one focuses mainly on areas and volumes. All right, so let's take a look at problem 1. It reads, let R be the region bounded by the graph of y equals e to the 2x minus x squared and the horizontal line y equals 2. And let S be the region bounded by the graph of y equals e to the 2x minus x squared and the horizontal lines y equals 1 and y equals 2 as shown right here. Part A is find the area of R. So this is a strategy I'm going to be using for all the problems. I'm going to first of all make a sketch. I'm going to orient my slicer radius, and then I'll label the functions and points of intersection, okay? And then I'm going to write down the formula that we are using, and then set up and evaluate. Now, let's take a look at the A part. Now, for every problem, you want to draw a brand new sketch, okay? Always sketch, 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 so that you do not make any mistakes with your with your values. Okay, so I'm going to try and make a sketch of this graph right here. In part A, we're looking for the area of just region R. Okay, so all I care about is this portion of the graph, that portion right there. So we region A, region R is bounded between y equals 2 and in the graph e to the 2x minus x squared. So let's call that 1. So let's say this is 2 right here. Okay, we have that, and then we have a piece of that graph. Let's say this is 1, and then this is 2, somewhere over here. And then we have a piece of the graph, something like this. Okay, so that's region R. That is what we want to find the area of. So next thing we're going to do is we're going to label the graph completely, okay? So since we are finding, if you look at how the function is set up, if we want to make a slice of the area of this region, we're going to slice in a vertical orientation, okay? So we're going to have vertical slices here. If we use the horizontal slice, we're going to be intersecting a function more than once, and it will be very difficult for us to set up an integral. All right, so we're going to orient it like this, top down. Now, since our slice, which has a thickness of dx, since it's oriented top down, it is perpendicular to the x-axis. So what does this mean? This helps me determine the formula, okay? Since we're perpendicular to the x-axis, that means the variable in my formula is going to be in terms of x, okay? So this function is going to be the top function. Let's label that f top as a function of x. Remember, we're perpendicular to the x-axis, and that is e to the 2x minus x squared. This is a function on the bottom, this line right here, f bottom. The function on the bottom is the line y equals 2, okay? And oh, we have to indicate the variable also. So f bottom of x, f bottom of x is equal to 2. All right, now what are limits of integration? Well, sweeping from this point of intersection to this point of intersection. So we need to know the value of our x left to our x right. Notice everything is going to be in terms of x, 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 because we are going perpendicular to the x-axis, okay? So this value right here will be our x left, which is equal to, we'll figure that out in a minute, and then we have our x right, okay? So let's figure out what these values are. All right, so this is a calculator section. So we're going to be using the calculator, the TI 89 and 83, to find the points of intersection, okay? If you know how to use the calculators to find the points of intersection, you can skip ahead of this part of the tutorial, but if you don't, go ahead and observe closely. All right, so the first function, let's use the TI-83 first. So for that one, you press the Y button, and then you enter the first function, which is e to the 2x minus x raised to the second power. Enter, and then the second function is just 2. Enter. Okay, let's go ahead and graph that. And then you have the line, and then you have the other. All right, so you have the two curves right there. Now I want to zoom into a window that, really shows me the area that I want to focus in on. So I'm going to use the zoom box. Go to the upper left corner so I can have a nice little window. Press enter, and then I'm going to go right past the curves, the two curves. Go down, press enter, and then it gives me a better view. It zooms into where I want to focus in on. Okay, so there goes the graph. Now we're looking for the points of intersection. Before we do that, let's go to the TI-89 and go over how to graph. All right, so you press diamond F1 for the graphing menu. You enter your function, which is e to the 2x minus x squared. That's the first one. The second one is y equals 2. And then we graph. Okay, while that graphs, let's go over here and calculate the point of intersection. So we have, to find a point of intersection, we're going to use trace. Okay, so second function trace gives you access to the calculator menu. So second function trace, intersect is option number 5. Press enter. It asks for the first curve. That's the first curve. Second curve, enter. And then it makes you to guess. So you take the cursor to the point where you want to find a point of intersection. Press enter. And then there goes your point of intersection. 0.446 is the x coordinate. And then you follow the same procedure for the second point. For the TI-89 titanium, the calculate menu is equivalent to the math menu here. So you press F5 for calculate. Over here, second function calculate gives you these, but these for TI-89, you have to press F5. Okay, and then you scroll down to intersection, and then it's similar to this first curve, second curve, and then TI-89 asks for the upper and lower bounds. Okay, let me escape this. I'm going to zoom in here so we can have a better view of what's going on. So go to the left, go up a little bit, enter, and then go to the right past the entire domain of the two graphs. Well, the domain that I want to focus in on. So just a snapshot of the domain. Okay, so there you have the second one. Using the TI-89, now we're going to find the points of intersection. So there goes the graph, and then F5 is our math menu. Scroll down to intersection, first curve, second curve, enter. Lower bound simply means you go to the left of the point of intersection. Upper bound, you go to the right of the point of intersection, and there you have the point of intersection there. Okay, so that's basically how you find the point of intersection using a TI-89 and TI-83. All right, so our x from the left, from the left side is 0.44661 to 4 decimal places, and x right is 1.5539. Okay, now we've sketched the graph of the region that we want to find the area of. We've oriented our slice, and we've labeled everything that we need to label. Next thing we're going to do is write down the formula. It's very important you write down the formula first. So in this case, we're looking for the area. The formula for the area is the integral from x from the left and x right um, of f of f from the top as a function of x, so f top of x minus f bottom of x dx. Okay, you notice we have x, 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 x because our slice is perpendicular to the x-axis, so everything is in terms of x. Okay, now we're going to just plug this value into plug in the values into the integral, and then we'll evaluate. Okay, so we're going to have the area is going to be the integral from x left, which is 0.44661, to x right, which is 1.5539, of f top as e to the 2x minus x squared. That's an exponent. Also e to the 2x minus x squared as f top minus f bottom, which is simply 2 dx. Okay, so all we do is plug this into our calculator and we'll get the answer. Okay, so I'm going to show you how to enter this integral expression into the TI-89 and the TI-83. Okay, let's start with the TI-83. So with the TI-83, you go to the catalog, second function 0, and then you go to the F functions, and then you're looking for fn int, that's function integrator. All right, so there goes the function that is going to calculate the integral for us. Now you enter the integrand, which is e to the 2x minus x squared, close that, minus 2. So there goes the integrand first, comma, your variable of integration is x, your lower bound is 0.44661, and your upper bound is 1.5539. And then you press enter, and then you get 0.5144. In the TI-89, let's go ahead and do it. This one, we have direct access to the integral function from the keys. So from the home key, we have second function 7 brings up the integral, and then it's exactly the same as this right here. You enter the function e to the 2x minus x raised to the second power, close that, minus 2. You're integrating with respect to x. Your lower bound is 0.44661, and your upper bound is 1.5539. Enter. And there goes your answer. Okay, so our answer is 0.5141. Go ahead and write that down. 0.5141. All right, let's take a look at the B part. All right, let's take a look at part B. We have to find the area of S. The area of S is basically this region right here. So like we are going to be using the same strategy as we used before. So we make a sketch of the situation, and then we're going to orient our slice. Since we're looking for area here, we're going to orient our slice. The slice that we want to, the orientation of the slice should be vertically, okay? So something like that, that should be the orientation of our slice. So that tells us that all our variables are going to be in terms of x. Okay, so this is the x-axis because our slice is perpendicular to the x-axis. This is dx right here, and our sweep is going to go from the left all the way to the right. Okay, now in this graph we have a composite region. Why is it composite? Well, the top and the bottom the top functions change. All right, so to make this obvious, what we're going to do is we're going to divide this region into three sections. So um, from here straight down, that's one section, and then this is another section right here. Okay, so we can call this 1, 2, and 3. So if we want to find the area of this region, we simply find the area of region 1, area of region 2, and area of region 3. Now what you notice here is that for region 2, this is f top. F top as a function of x is equal to 2. But for region 3 and region 1, this is f top. The f top here is the exponential function, which is e to the 2x minus x squared. And over here, in region 1, we have the same f top. Okay, so we have to split this integral into three different expressions. Okay, so the area is going to be the area from region 1 plus area of region 2 plus area of region 3. Okay, so let's go ahead and write our formula. Remember, you want to write your formula next. So I placed the strategy guide again down there to guide us. So let's write down what the formula is. The formula for the region between two curves oriented vertically is for area, area A is the integral from x from the left, x left to x right of f top as a function of x minus f bottom as a function of x dx. Okay, so that's the formula we're going to be using. Now, in this problem, the area is going to is basically the area of region 1, A1, plus area of 2 plus area of 3. We are going to be applying this formula 3 times to find the area of region 1, 2, and 3. Okay, so let's go ahead and set that up. Our area is going to become area of region 1 will be the integral, so we can extend this down here. Region 1 ends at the first point of intersection, which is 0.44. Region 2 ends at the second point of intersection. And then region 3 is just at 2. Okay? Alright, so the area of region 1 is going to be the integral from 0, that's the x left, to x right, 0.446, times function on the top. Now for region 1, the function on top is e to the 2x minus x squared. So that's going to be e to the 2x minus x squared. F top minus f bottom. F bottom is 2. So that goes your first. Actually, no, this is f top. F top is 2, f bottom is 1. So f bottom, gotta be careful with that. F bottom as a function of x is 1. Is equal to 1. The f bottom doesn't change for the entire domain, okay? So f bottom is 1, so f top minus f bottom, so that minus 1. Alright, dx, that's the area of region 1. Region 1 is this region right here, to the left of 0.446, plus area of region 2, which will be the integral from 0.446 to 1.5539. So 0.446 all the way to 1.5539. And the integrand, f top minus f bottom. F top is going to be 2, f bottom is 1. This is a rectangle, okay? So an easy way to do this would just be to find the area of this rectangle 1 times the length of the rectangle, or we can set it up using integrals. F top is going to be 2 minus f bottom, which is 1 dx. Okay, so that plus the third region 3 right here. Let's go ahead and set up the integral for that expression. So that will be the integral from 1.5539 all the way to 2 of f top, which is e to the 2x minus x squared minus f bottom. F bottom is always 1 quantity dx. Okay, so this is an expression for the area of these three regions. This is one way of doing it. There's another method where you find the entire area of r plus s, and then you subtract the area of angle r as the result we got in the a part. Okay, so we just set it up like this, input it into your calculator, and you should get the right answer, which is 1.546. So it's approximately 1.546. All right, let's take a look at the C part. So for the C part, it says, write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated about the horizontal line y equals 1. So we're still using the same strategy. Want to sketch the graph. In this case, we're focusing only on region R, so sketch only the relevant components. And we also, of course, want to draw our axis of rotation. Okay, so there goes our axis of rotation. Now, since we are rotating around a horizontal axis, our slice is going to be the radius. It's going to be the radius of the washer. Okay, so let's go ahead and sketch our washer. It's going to be oriented in an orientation perpendicular to the axis of rotation. So there goes the washer right there. Okay, so what does that mean? Since we're perpendicular to the x-axis, again, that means that all our variables will be in terms of x. Okay, so we're going to have, if we trace that down, that will be our x left. We already know what that is, x left. And then x right will be this point of intersection right here, x right. And then we're basically rotating this region around this axis of rotation right here. Okay, all right, now we have our orientation. Let's go ahead and label some more. This is going to be our f top. We already know what that is. F top is e to the 2x minus x squared, and then f bottom is simply the linear function, which is 2. Okay, so there you have it. And of course, we know what x left and x right are. X right is 1.5539, and x left is 0.446. Okay, all right, so now let's go ahead. We have the setup. We're going to go ahead and write down the formula. Okay, so in this problem, we're looking for the volume. So let's go ahead and write down the formula that we're going to be using here. So what's the formula for a solid of revolution? The volume of a solid of revolution. So our volume V is going to be pi times the integral x left to x right. So x left to x right of the outer radius square. So our outer as a function of x square. So if we have pi times the outer radius square, that will be the area of the outer disk. Okay, so we're going to have the area of the outer disk minus the area of the inner disk. So that's going to be radius of the r inner as a function of x square. Okay, and then the whole thing dx. So that's the formula for the volume of a solid of revolution, where the axis of revolution is a horizontal line. In this case, it is y equals 1. All right, so now that we have the formula written down, let's go ahead and find out all the components. All we need that we do not know are just the outer radius and the inner radius. Okay, so let's go ahead and set up our integral. Now to find the outer radius is simply the distance from the top function to the axis of rotation. That's our outer. Okay, so let's go ahead and determine what that is. So this length right here, that's our outer. Let's go ahead and write it down. So our outer is going to be f top minus 1. Okay, f top minus 1. And then next thing we need is the inner radius. The inner radius is going to be, so this right here is our outer. And then our inner radius is going to be the distance from the F bottom to the axis of rotation. So this right here is going to be our inner radius, that length right there. Okay, so it's going to be F bottom minus 1 for our inner radius. Put that, scroll up, put that up here. So our R inner is going to be F bottom minus 1. That will be our inner radius. Okay, so let's go ahead and write it down. So our R outer as a function of x is going to be F top, as we calculated here. F top is the original function, e to the 2x minus x squared, minus the axis of rotation, which is 1. And then our R inner is going to be, as a function of x, is going to be 2 minus 1. Okay? All right, so all we simply do is put all these into our formula. All right, so we're going to put everything together in the formula. Find the volume. V is going to be pi times the integral from x left is 0.4461 to x right, which is 1.5539 of our outer. We already determined what that is, e to the 2x minus x squared minus 1. That's our outer. We're going to square that, of course. Our outer squared. Remember the formula is our outer square minus our inner square. So our outer square minus, and then our inner square is 2, simply 2 minus 1. And we also have to square that. This entire thing dx. And that is the expression for the volume when region R is rotated about the axis y equals 1. Thanks so much for taking the time to watch this presentation. I really appreciate it. Feel free to subscribe to our channel for updates to other tutorials such as this. More clips can be found on mathcoachserve.com.